Hi, good afternoon. It's great to be here and share my talk at SigOpt Summit. My name is Ke. I'm a principal AI engineer at Intel and currently leading the Applied ML team at Software and Advanced Technology Group. My talk today is faster, better training for recommendation systems. This is a summary based on the work we did for MLPerf v1.0 training submission this year. And here is today's agenda. First, I will talk about recommendation system overview, and in particular, the Facebook DLRM model. In the second part, I will introduce how Intel does for MLPerf v1.0 training scale out for DLRM model, including data and model parallelization, efficient data loader, and optimizer improvement. After that, I will talk about how to use SigOpt hyperparameter optimization tool to improve the model convergence. I will conclude the talk with a summary section. If you are familiar with the deep learning workload, you probably already know that recommendation is one of the biggest AI workload running at data center. Things like personalized Amazon product recommendation, like nearby restaurant, like hottest vacation plan, they are all running at running recommendation systems back in data center based on your real-time personalized data input. A typical recommendation system takes two types of data as input. One is so-called numerical dense features. Examples like age, like number of purchase per month, like active minutes per day. And you are on a certain application. And the other type of input is categorical sparse features. Examples like gender, like a product ID, like location. Sparse feature usually is very large due to its nature. And with both dense and sparse feature as input, they pass through the recommendation models and generate an output. The most commonly used output of the recommendation system is the probability of a click, also called as CTR, click-through rate. It indicates with all the dense and sparse context feature presented now, whether the user will end up with accepting the recommendation or not. And you can imagine already why it's so important to build the best recommendation systems in order to generate the best business values. Hyperscalers and many other enterprise customers are working very hard in this domain. As a result, there are many SOTA models for recommendation system, such as NCF, Wide and Deep, DIN, and the DLRM. Also, there are many industry benchmarks. Two popular examples are Twitter's annual Rexis challenge and MLCom's MLPerf benchmark. Recommendation system is so important, yet there are many technical challenges to solve. Every accuracy improvement directly translates into business values. Hence, the accuracy requirement is very high. Because of that, oftentimes the recommendation models are very big and the data set is huge in order to cover more scenarios. Model retraining is another challenge in order to get the most up-to-date models based on user data. In the following slides, I will focus on DOI model for MLPerf training and how Intel optimizes it to get the best scale-out training performance. DLRM is a SOTA model and part of MLPerf training benchmark. In high level, its model topology actually is quite simple. The dense feature goes to the bottom MLP, and the sparse feature goes to embedding lookup tables. After that, they interact together and feed into top MLP, and then output as the click probability. Each block has its own characteristics as color-coded for memory, communication, and compute bounded. The data set used for DLRM training is 1.2 terabyte critical data set. Model size is huge because of the sparse layers. In total, if running it on a single instance, the required memory will be more than 100 gigabytes. On the other side, however, the 26 embedding tables are extremely imbalanced. Four biggest tables have more than 40 million entries, while the smallest one only has 3 and 4 entries. With all this, DLRM poses unique challenges on distributed training because of the need to balance compute, memory, and communication. The model is so large so that we will need to use both model and data parallelization in order to speed up the training. However, when we do so, it means that we are increasing the global batch size and reducing the number of weight updates per epoch. It then introduced another challenge on the model convergence. To tackle these challenges, we implemented an efficient scale-out solution using data and model parallelization, a novel Dataloader, and a new hybrid splitSGD plus LAM optimizers, and efficient hyperparameter tuning for model convergence. I will introduce each of them in the following slides. Now let's talk about data and model parallelization. It's straightforward to use data parallelization to split the dataset and speed up the time to train. However, this poses the high memory and communication requirement because of those large embeddings. To reduce the communication overhead and the memory requirement on each device, we use a hybrid parallel distributed training solution. The embedding table is divided into 10 small and 16 large embedding tables. For model parallelization, model instances would hold a local copy of part of the large embedding tables. For example, if we use 8 sockets and 1 instance per socket, then every instance will hold 2 large embedding tables. For a 16 socket system, every instance will only hold 1 large embedding table. All-to-all collective communication is used to exchange embedding information between ranks. For data parallelization, bottom MLP, top MLP, and 10 small embedding tables are replicated in every model instance, and all reduced collective communication is used to average the gradient between ranks. So the limitation here of this approach is that the number of instances cannot exceed the number of large embedding tables. For MLPerf DLRM, we only have 16 large embedding tables, which means that we cannot scale to more than 16 instances. To improve the scaling further, we use vertical split embedding-based model parallelization. So in this embedding vertical split method, large embedding tables are vertically split into multiple embedding tables with the same entry number as the original. And each table has a subset of the columns in the original table. We then let each model instance hold one of the split tables and use all-to-all communication. We put 1 embedding tables on each model instance, look up each table with global batch, then use all-to-all to transpose the lookup entries among instances. After that, we would concatenate entries belonging to the same original embedding table, and then go through the up MLP layers as a data parallel approach. So from this, we can clearly say the advantage of our vertical split embedding-based hybrid parallel approach. First, because the vertical split of big tables will reduce the communication overhead of models with embedding tables. This reduces time to train and allows more efficient scaling of multiple model instances. Second, it obviously reduces the memory requirement. Total 26 embedding tables require more than 100 gigabytes memory for a single node training. With simple hybrid data and model parallelization without vertical split, it still requires more than 25 gigabytes on each socket. While we scale out to 64 ranks using the solution just described, we only need about 6 gigabytes per instance. Therefore, the vertical split embedding optimization is also a general solution to train workload with oversized embedding tables. So far, I have described the vertical split embedding table to scale to more ranks and reduce memory footprint. Large embedding table need to look up global batch size entries with model parallelization, which means that we also need to read global batch size input from disk. Therefore, I/O is a potential bottleneck on multi-socket systems. Here, a novel model parallel data loader is proposed to reduce this overhead. The data loader will only read the local batch size inputs, which is a fraction of global batch size input, and use O2O communication to get global batch size input. I don't want to dig into very detail for this due to the time constraint, but if anybody has interest to know more, we can discuss offline or check our blog. The next optimization area is around optimizers. In order to support large scale out training on Xeon cluster, we need to make certain improvements in order to speed up the time to train. In particular, we want to benefit from low precision format BF16 for performance. We also want to ensure proper model convergence once we scale out. So let's first talk about BF16 support and the memory optimization by using splitSGD. BF16 not only speed up the forward and the backward computation, but also requires only half of the memory size. However, in the optimizer stage, we will have to keep a FP32 master weight in order to maintain necessary accuracy for model convergence. Hence, you can see it gives us a memory consumption challenge because it actually requires more memory compared to FP32 base training, which is shown in the above figure. The solution here is to use split version of SGD optimizer proposed by our Intel Labs team. Because BF16 share the same 8-bit exponent part and only sacrifice precision in the mantissa part, we actually only need to store the lower 16-bit mantissa from the original FP32 weights. Then combine it with BF16 as higher 16-bit to get the full 32-bit FP32 number. Through this way, we are able to keep the full precision master weight, as well as to reduce the memory consumption and the traffic. The default SGD works perfect for DLRM when the scale out is not large. However, when system scale outs with more nodes, either you will keep the global batch size same or reduce the local batch size, which is not good for computing efficiency perspective, or you keep the local batch size same, increase the global batch size when scale out more. In the latter case, it introduces the convergence challenge. For example, when increasing the batch size from 32K to 128K, the default SGD optimizer won't converge the model at all. And the increasing learning rate for larger batch size makes training unstable. And the learning rate warm-up only works for up to a certain batch size. Hence the introduction of LAM optimizer, which is, in simple summary, is layer-wise adaptive plus Adam optimizer proposed by Google Brain team. They introduced the new concept called trust ratio. So with this trust ratio, usually warm-up is not needed or not help much if learning rate is scaled by this. The trust ratio is defined as below. So R1 is the norm of the weights, and R2 is the norm of the Adam update term. So eventually, the base learning rate is scaled by this trust ratio. The full weight update term is shown at the right side. What it means is that when the weights are small, we take a small step not to make a big mistakes initially. When weights are large, we take a bigger step in order to accelerate the convergence. So why this? is because we want to have the gradient and the weight in a similar dynamic range. Because the batch size is so large that oftentimes the accumulated gradient from this mini batch is much larger or sometimes much smaller than the weight itself. This is exactly the phenomenon the Google Brain team observed and figured out the simple way to solve it. So in summary, LAM is just another level of adaptation on top of ADAM. Adaptation, base learning rate per layer plus adaptive moment. But this is extremely useful for large batch size training convergence. So with BF16 and the memory optimization for splitSGD and the LAM optimizer for large global batch size, now we have both to form hybrid optimizers for DLRM in order to get all the benefit. In particular, LAM optimizer is applied to dense layer, including top and the bottom MLPs, and those smaller dense embedding layers for the purpose of better convergence. And the splitSGD is applied to those big sparse embedding layers. The code snipped is in the up figure, which is straightforward. By doing this, we optimize for memory consumption, convergence, and performance, which leads to the speed up for the time to train metrics that MLPerf cares most. And now let's talk about model convergence. During the modeling practice, we have many design choices that needs to be finalized through like both heuristic knowledge as well as some automation tools. So even if you have a well-trained FP32 model, when you retrain or fine-tune it for a downstream task, or maybe optimize for a particular hardware platform, oftentimes you cannot use the original hyperparameter set, and you will need to tune a new one in order to meet your business requirement. Such example actually is very common, such as you scale out the training with more hardware resource to speed up the training, meaning you now have big batch size, or you have to use a low precision format such as BF16. And sometimes you change the optimizer, or you are given a new data set to optimize for a particular use case. Or sometimes you simply want to tune the parameters further to get a better time to train. All this leads to a very strong requirement to have a good hyperparameter optimization tool or service. As a data scientist, what I'm expecting HPO tool should provide: first, a flexible search space definition supporting different data type, transformation, constraints, condition, something like that. And also capable of large search space to tackle complicated problem. And second, such tool is expected to be built on an efficient model so that it can converge and find the global optimal point much quicker for a black box optimization problem. And that's actually the unique advantage. Also, in order to speed up the execution, parallel execution feature is required, as well as to early stop unpromising trials. Because by comparing with earlier results, you can already predict whether the current one is going to be much worse or much better. In some situations, the optimization may contain multiple objectives, such as to optimize both performance and accuracy. Then multi-metrics support is required. And last but not least, a nice dashboard and insights will save tons of work for a data scientist. And fortunately, we have SigOpt as part of Intel's machine learning toolset. It is a hosted service and can support all the requirements I just mentioned. So let's talk in more details how I use SigOpt tool to help this DLRM training convergence problem. So this page shows the HPO tuning setup. The auto-tuner abstracts the HPO tuning process between HPO tool and the tuning workload. It takes search space definition for the tuning workload, gets suggestion from HPO library, running the tuning workload with this parameter, and send back the result matrix back to the HPO, and then get the next suggestions. This is an iterative process until predefined tuning budget is reached. In this DLRM case, the searching space contains 4 tunable variables: learning rate, warm-up, decay, and optimizer choice. It's a big workload, and I use Intel internal Xeon CPU cluster for this tuning exercise, with parallel experiment features to speed up the tuning. So efficiency improvement for any kind is super helpful in saving the cost as well as to improve the time to train. Several features I used during this tuning exercise, such as learning curve regulator, which is about anomaly detection for learning curve, right? And like overfit detection. Also, I use the pruner to early stop unpromising experiments. Pruners such as medium, such as percentage, and usher are used in my experiment. And SigOpt provides very nice dashboard for the summary and insights for your tuning experiments. For this DLRM tuning task, to simplify the problem, we set the tuning target to optimize the AUC accuracy score only as a single matrix optimization problem. So from the left side experiment improvement figure, we can clearly say SigOpt is about it is able to find the result much quicker and better compared to other open source HPO frameworks. The DLRM AUC convergence threshold is 0.8025. SigOpt only takes for a few experiments that exceed this threshold. Within the experiment budget, the optimization result gets improved further, and eventually it's able to find a very good AUC score that helps the DLRM convergence quicker. The upside figure shows the parameter importance. This is very useful for data scientists to understand which parameter should be tuned and which might not need. In this particular case, we know learning rate and warm-up are very important because when you scale out, the global batch size increases and you will definitely tune it to get a proper value. Decay on the other side is less important, which indicates in future for such kind of similar problem, you don't need to tune decay so that to reduce the tuning space and to save computing cycles. So putting together all the above mentioned optimization, we implemented this DLRM training on our AI cluster called Catalina. It has 16 nodes in total, with each node having 8-socket Cooper-Lake Xeon CPUs. We use PyTorch, IPEX. IPEX stands for Intel PyTorch extension, and the 1CCO libraries. Here, x-axis is the number of sockets, and the y-axis is the time to train in minutes. So the first column bar shows the close division result, which takes about 2 hours to get a convergence if we only use 4 sockets with 32 global batch size. The middle column bar shows the V0.7 training submachine result last year with 32 global batch size and with splitSGD optimizer. It requires like 45 to 48 minutes. And so when we use LAM to enable 256K global batch size and the vertical split embedding table to scale out to 64 sockets, it only took 15 minutes to convert, so which is a 3x speed up compared to last V0.7 result. So with the upcoming SafaRapid and the AMX deep learning accelerator, so we are expecting more improvements. Okay, now let's summarize what I talked today. So first, we demonstrated how we optimize the DLRM training workload on Xeon cluster and get a balance among compute, memory, and communication to achieve the efficient scale out. And even though we have hybrid data and model parallelization, we have efficient data loader and hybrid optimizers as individual improvement, this final result cannot be easily achieved altogether without the great HPO tool, SigOpt. So SigOpt HPO tool is crucial for faster and better training for DLRM recommendation system. This concludes my talk today. Thanks so much for listening. Thank you.